All right, we're going to dive into a question in physics that is, well, hiding in plain sight. I want you to picture a flowing river. From where we stand, it looks totally smooth, right? Continuous, like one single thing. But is that what's really going on? Yeah, what if we could zoom way, way in? I mean, past the surface, smaller than the tiniest drop, all the way down to the nanoscale. What would we see then? Well, that smooth, perfect flow would just dissolve. It would turn into this wild, buzzing, chaotic dance of individual molecules, a whole universe of particles bouncing off each other. So which one is it? Is the river this serene, flowing thing we see with our eyes? Or is it that microscopic mayhem? How do we even begin to make sense of that? Which model, which picture is the right one? Well, here's the thing. The right description, it totally depends on the question you're trying to answer. Physics really is the art of simplification. It's about making a smart choice about which version of reality is the most useful for your problem. We call it idealization. Here's a great way to think about it. It's like a pointillist painting. From way across the room, you see a complete, smooth picture. A park, a boat, whatever. But you walk right up to it, and what do you see? Just thousands of tiny, separate dots of color. It's the same painting, but the reality you see depends entirely on your perspective, and that's exactly what's going on with fluids. So let's look at those two different views. So on one side, you have the continuum view. That's the painting. It's our everyday experience where we can talk about the pressure or the speed at any single point in the water. But on the other side, you've got the discrete view. Those are the dots. This view acknowledges the physical reality that, hey, this fluid is actually made of individual molecules. Things like pressure aren't some magical property. They're really just the average results of trillions of tiny collisions happening every second. Okay, so how in the world do we decide which one to use? When is it okay to just look at the painting, and when do we absolutely have to focus on the individual dots? Well, it all comes down to a game of scales. First, we need to understand the world of the dots. And our ruler for that world is something called the mean free path. We use the Greek letter lambda for it. It's super important. It's just the average distance a single molecule gets to travel before it smacks right into a neighbor. And just so you know, in the air around you right now, that distance is about 68 nanometers. Incredibly tiny, but definitely not zero. Next, we need a ruler for our world, the big picture macroscopic scale. We call this the characteristic length, or delta. This is just the size of the thing we care about. It could be the diameter of a pipe, the wing of an airplane, heck, it could even be the little swirl you see in your morning coffee. And here's where it all comes together. The deciding factor, the key to this whole thing, is what happens when you compare these two scales. We just take that tiny, microscopic distance, lambda, and we divide it by our big, everyday length scale, delta. And that simple ratio has a name, the Nansen number, or Kn for short. You can think of it as the ultimate referee in this game of scales. It's just a number, no units, but it tells us exactly which rulebook of physics we need to grab off the shelf. This chart here lays out the rules of the game perfectly. Check it out. When the Knudsen number is really, really small, we're in what's called continuum flow. Molecules are bumping into each other constantly, so they act like a group. Perfect for the continuum model. But when the Knudsen number is really large, the molecules hardly ever hit each other. They're more like lonely bullets flying through space. That's free molecular flow, and you absolutely have to use the discrete model. And that bit in the middle, where the Knudsen number is about 1, that's the transition flow, and it's incredibly complex. Okay, so that's all the theory. But what does this actually mean out there in the real world? How does this choice really play out when we're trying to build something or understand how the universe works? Now, what's really fascinating here is that the Knudsen number doesn't live in a vacuum. It's actually connected to two other really famous numbers in fluid mechanics, the Mach number, which has to do with speed, and the Reynolds number, which has to do with turbulence. This little relationship is a powerful bridge that connects the microscopic world of molecules to huge things like high-speed flight. It's pretty cool. And this connection has massive consequences. I mean, huge. Let's follow a spacecraft coming back to Earth. At the very top of the atmosphere, the air is super thin, which means a low Reynolds number. At the same time, the craft is screaming through the sky at hypersonic speeds, so its Mach number is gigantic. And what does our little formula tell us? A high Mach number divided by a low Reynolds number means the Knudsen number is enormous. And that means our normal, everyday rules of fluid dynamics, the continuum model, they just fail. They don't work at all. So think about what this means for the spacecraft. Way up high, it's in a free molecular flow. Individual air molecules are just pelting the heat shield like tiny little projectiles. As it gets lower, it enters that super complex transition flow, and only when it gets much, much lower into the thicker atmosphere does the air finally start behaving like the continuous fluid we're used to. So the engineers have to design a vehicle that can survive a trip where the fundamental laws of physics are literally changing around it as it falls. So, what's the big takeaway here? It's all about choosing the right tool for the job. You wouldn't use a microscope to look at a galaxy, right? And you wouldn't use a telescope to study a single cell. It's exactly the same idea in physics. For pretty much everything we build and experience right here on Earth, the continuum model is the perfect tool. The distance between air or water molecules is just so tiny compared to the size of a plane or a weather system or a plumbing pipe. So yeah, for designing airplanes or figuring out the weather, we can safely treat fluids as a smooth, continuous thing. But, and this is a big but, for the extremes, for the absolute edges of science and technology, we have to go back to the dots. For spacecraft way up high, for gases in a vacuum chamber, or for those incredibly tiny little machines on microchips we call MEMS, the size of the system is so small that it starts to approach the mean free path. And when that happens, we have to go back to the beautiful chaos of the molecular world to get the physics right. So this journey, from the big picture down to the tiny parts and back again, it really shows us that our physical reality is all about perspective. It's a matter of scale. And that leaves us with a pretty mind-bending question, doesn't it? If the smooth flow of water is just an illusion, a trick of statistics, what else do we see as continuous that, at its deepest, most fundamental level, is actually made of dots?